Over the last couple of classes, we've talked about various ways to deal with differential equations. So we started out by solving some separable differential equations, but we recognized that not every differential equation is separable, and hence we don't know how to solve every differential equation. So we talked about a graphical way of looking at differential equations last time via direction fields. And today we're going to talk about a numerical way of understanding solutions to differential equations. And this is something called Euler's method. I know that this word, Euler, does not look like Euler, but that's actually how it's pronounced. It's the name of a mathematician. So let's just jump into an example here. And I'm going to use this example to show you how this method works. But the details might feel a little cloudy as we go through this example. So don't worry, we'll do more examples where the details will be more understandable, hopefully. But I want you to see where the process comes from. Okay. So in an Euler's method problem, we're going to be given a differential equation and an initial condition, and then we're going to try and approximate the solution at another point, okay? So we see that this differential equation is not separable because of the addition between the x and the y. So we can't solve this one. And so we need other methods, which is why we're going to use Euler's method. So what I'm going to do is I'm going to kind of look at the direction field and use that. I'm just going to look at the direction field in a very small portion. So I'm going to start with that point 0, 1, because that is my initial condition. The x value is 0, the y value is 1. And I'm going to draw my direction field at that point. So when I plug 0, 1 into my derivative, I'm going to get 2 out. So the slope there is 2. So I'm going to draw my little line segment, and I'm actually going to draw a long line segment here. I'm going to go all the way until I bump into another point. So there we go. I bumped into a point. And so let's see what happens here. So what I'm going to do is I'm going to write the equation of that line that I just drew. That line is the tangent line at the point 0, 1, and it has a slope 2. So we have the point 0, 1, slope 2. Okay, and then I'm actually going to leave the x minus 0. I'm not going to simplify that for a reason that we'll see in a minute. Okay, excellent. And so the new x value that I'm at now is 0.5. So I want to make sure that this y value is indeed 2. It looks like we got to the 0.2, but let's see. So if I plug in 0.5 for x, then what I get out is 1 plus 1 is 2. Okay, cool. Excellent. So what I did here was I drew my tangent line until I bumped into a new point. My new point was half a unit away from my original point because that was how I created this direction field graph. And so this is going to be one of the things that we're given in an Euler's method problem is it's going to tell us how often we want to redirect. In this case, we're going to redirect every 0.5 units. What this is saying is that delta x is 0.5. This is my change in x values. How often am I going to bump into a new point and then draw my direction field again? Okay. So we are at the new point 2. What this is telling us is that the y value at 0.5 is approximately 2. This is our approximation based on using the direction field, okay? But that's not what we wanted. We wanted to approximate y of 1, so we're going to need to do a little bit more work. Before we do that, let me point out a few things here. My approximation for y of 0.5 came from, let's see what it came from. The 2 was the slope at my original point. And let me say at the previous point. The 0.5 minus 1 or minus 0, that's 0.5. That was just my delta x. And the 1 was my y value, my previous y value, which I oftentimes call my old y value. Okay, so this format that I have here, slope at previous point times delta x plus previous y value, that's actually going to be Euler's method. So we're going to see this format several times, but let's see why in just a second. Okay, so what I'm going to do now is I'm going to take that point that I bumped into, this point 0.52, and I'm going to draw the direction field line from this point. Okay, so I need the slope at that point, and let me do this in red. So the slope there will be 0.5 plus 2 times 2, which is 4.5. Okay, so we're going to have a super steep slope here. So steep that, I don't know, I'm not even really going to draw it. So we're going to go all the way up until eventually, until eventually we bump into some point with x, or with, yes, with x value 1. Okay, so we're going to bump into some point up here, and the question is, what's that point? So the way that we can find that point is we know that we started at the point 0.52, and our slope was 4.5 because that was this point. And so let's write the equation of this line. Okay, so the equation of that line is y minus 2 is 4.5 times x minus 0.5. Again, I'm going to rearrange this, but not really simplify things. Plus 2, just add the 2 to both sides. Okay, so now what we wanted is we want to know what is the y value going to be when x is 1. So we're going to plug in 1 for x. So we're going to get y is 4.5 times 1 minus 0.5 is 0.5 plus 2. Okay, so we can get a number out from this. This ends up being 4.25. Okay, so that it would be our y value when x is 1. So this is our approximation for y of 1. Okay, so let's see what we did here. So what we did is we started at our initial condition. We drew the tangent line at that point, which is really, we followed the direction field at that point until we bumped into a point at our new x value. Okay, and then we redirected from there. We said, okay, well now, which way is the curve going from here? And we kept going until we bumped into a y value at 1. Okay, if we had redirected more frequently, then we would have had a better approximation because we would have been following our curve more closely. So if instead of going a whole half a unit away in that first iteration, I had gone a quarter of a unit away, and then I just did more iterations until I got to 1, I would have a better approximation. Okay, again, let's look at the format of how I got to this approximation, or to like this final approximation. So the 4.5, that was the slope at the previous point. So at that point, 0.52, that previous point. The 0.5 was our delta x, and the 2 was our previous y value. Usually I call it my old y value. Okay, and notice that's the exact same format that we had over here. So this is exactly how Euler's method is going to work. So if we scroll down, Euler's method is going to give us a way to approximate y values to the solution of an initial value problem. So the general format is that my new y value is the slope at the old x and y times delta x plus my old y value. Notice that's exactly what we did before, except for I was saying previous point instead of old point. Okay, so really what we're doing with Euler's method is we're looking at tangent lines. We're following tangent lines along a curve. Okay, so let me show you how this actually works in practice, because usually we don't actually draw tangent lines. Okay, so let's see what happens here. Okay, so this first example says, use Euler's method with delta x equals 0.25 to approximate y of 1 for this initial value problem. So the way that I usually set this up is I do a 3-column table with x, y, and then the slope at that point. Okay, so my x and y to get started come from my initial condition. So my initial condition in this point gives me the 0.01. So my initial x is 0, my initial y is 1. My delta x is 0.25, which means that my x values are going to increase by 0.25 at each step. And I want to go all the way until I get to x equals 1. So my x values are going to be 0.25. I add 0.25 to that to get 0.5. I add 0.25 to get 0.75. And then I get to 1. Okay, so that's where I'm going to stop. That's where my table ends. Okay, and what I'm looking for is I'm looking for the y value that corresponds to x equals 1. So whatever goes in this box is going to be my final answer. Okay, so what I'm going to need is I'm going to need the slope at each of these points. So the slope is going to come from the differential equation. So that's how we're going to fill in this side of the table. Okay, so when x is 0 and y is 1, my slope is going to be 0 plus 2 times 1. Okay, we notice this is the same differential equation from the previous page. So we're just doing a better approximation here because we're using delta x equals 0.25. Okay, so we're going to get 2 out there. Okay, so now we use Euler's method is what we use to find the y values. Okay, so this next one, Euler's method tells me that the new y value is the slope at the old x and y. So that's my previous slope, which was 2. Let me color code this. So the 2 is coming from here, times delta x, which was 0.25. That's just our delta x, plus the previous y value. So that was this one. So 1 plus 1. Okay, so this is how Euler's method works, is the previous slope times delta x plus the previous y value gives me the new y value. So if I compute that, I get 1.5. Okay, the only problem with Euler's method is that it's really easy to make mistakes along the way with calculations, so just be very careful. Okay, and so now I'm going to calculate the slope at this new point. So I have the point 0.25, 1.5. So I'm, again, using my differential equation. So I'm going to have my x value is 0.25 plus 2 times 1.5. That is going to give me 3.25 as my slope. Okay, now I use Euler's method to compute my new y value. My new y value is my slope at my old point, so my 3.25, so this slope, times delta x, that's always going to be the 0.25, plus my previous y value, which was 1.5. Okay, so trying to color code this so you can see where these come from. Okay, this is where you need to give yourself lots of room on this y line. So this ends up being 2.3125. Go ahead and keep lots of decimal places here, because if you round along the way, then that rounding error just propagates through these problems. Okay. So, okay, let's keep going. So now my slope using my differential equation is going to be 0.5 plus 2 times 2.3125, which is going to give me 5.125. Why don't you finish this table? Okay, so you finish it and then watch me finish it in a minute. Okay, so now Euler's method tells me I take my previous slope, 5.125, times delta x plus my old y, which I'm not going to rewrite, 2.3125. Okay, I did rewrite it. And when I do that, I get 3.5938. Okay, we're getting close. Again, if I color code my pieces. Okay, now I calculate my slope. I have 0.75 plus 2 times 3.5938. Remembering that our slope is always coming from the particular differential equation in this problem. So the only reason that I'm doing x plus 2y here is because that's what the differential equation told me. Okay, so I'm getting 7.9375 out here. Okay, so now we're at our last step. So I'm going to do my old slope times delta x plus my old y. And when I do that calculation, I get 5.578. This is my final answer. We do not need to find a slope at the last line because we don't care. We're not doing another iteration. We just cared about that y value. So what this is telling us is that our y value at 1 is approximately 5.578. Okay, this should be a better approximation than we got on the previous page because we recalculated more often because our delta x was smaller. Okay, phew. Okay, that's a lot of work. One more example here. And then we'll do lots of practice in class. So really, it's not hard, hopefully, it's just tedious. Okay, so this one says that we want to use Euler's method with 2 steps of equal size. So we're going to have to translate that into a delta x in a second to approximate y of 3.2, where our differential equation is this and our initial condition is this. Okay, so let's try setting the table up, leaving lots of space for y just in case we need it. Okay, so my starting value is 3, 2. That comes from my initial condition. And I want to end at 3.2. Okay, so our delta x goes from 3.2 to 3, and I want 2 steps. So we're going to do the length of the interval over the number of steps. So this is going to give me 0.2 over 2, which gives me 0.1 is my delta x here. So I'm going to have 3.1 as my middle x. Okay, you can always fill in the x's to get started. Okay, so now my slope, I'm using this differential equation now. So my slope is going to be 2 times square root of 3, which is not a pretty number. That's 3.464. Okay. Now I'm going to take my slope, 3.464 times my delta x, which in this case is 0.2, delta x, previous slope, and then plus my previous y value, which was 2. Okay. And so when I calculate that, I get 2.3464. Okay. Now we need to calculate the slope. So I take my y value, 2.3464 times the square root of my x, 3.1. That gives me 4.131. You should be double checking my calculations. Okay. So now I take, whoops, wrong color. I take this one, 4.131 times my delta x plus my old y value, 2.3464, and that's going to give me 2.7595. This is my final answer, remembering that we don't need to find another slope. So this tells us that y of 3.2 is approximately 2.7595.